Hello, everyone. Thank you to this. Thank you for joining this session, this seminar. Today, I'm pleased to introduce Dr. Latévi Lawson. He is a postdoctoral.
So you speak there. Sorry.
I was saying, it's my pleasure to introduce Dr. Latévi Lawson.
Please.
The postdoctoral. Is it okay there?
Yes, it's okay now. Please go ahead.
Okay. He's a postdoctoral researcher and a tutor at the African Institute for Mathematical Science in Ghana. Before that, Before that, he works as a teaching assistant at the Department of Physics at Université de Lomé. He obtained his master and PhD in mathematical physics from Institut de Mathématiques et de Sciences Physiques in Benin. His research interests include non-commutative quantum mechanics, representation theory of differential operators, and machine learning. Today, we will present on the topic path integral in position-deformed Heisenberg algebra. Latévi, over to you.
Yes, thank you very much, Chanel, for this introduction. And thank you for the effort that you have made to arrange this conference for me. It's very grateful for me to present here. I used to follow all the conference in this seminar, and it's a pleasure for me to present one of our recent paper here. I would like also to thank Professor Francesco, who did a lot he contributed a lot for the quantum theory. And the first time I didn't meet him in person, but I know him through his paper, The Future of Quantum Biology. Is the paper that let me know him and follow him since then. Thank you for that. So this paper, this work is a recent work published in Annals of Physics, and it's a joint work with Prince Osei, which is who is the center president of AIMS Ghana, who also is my supervisor here for my postdoctoral. Komi Sodoga, who is my former lecturer at Université de Lomé, who is a lecturer over there, and Fred Soglo, who is a PhD candidate at AIMS Ghana. So the talk, sorry, oh, okay, sorry. So I would like to start by a difficult question, asking that, is it possible to move from Accra to Stellenbosch in 1 second? If something like that is possible. Okay, at first glance, this question seems very stupid, no sense, because it's not possible to move in 1 second from Accra to Stellenbosch. Now, let's assume that what I'm saying is true. If it's true, how can we join? How can you move from Accra to Stellenbosch, which is the technology that will allow us to join, to make this motion in 1 second? So this will be the motivation of my talk. We are going to show that, okay, it's possible in theory, and look now for how it can be practiced in the real universe. If I take this moving, which is realized by the Stephen Gould, the name of this moving, which is entitled a jumper, we can find in this moving that, okay, the actor have a sort of superpower which allowed him to teleport from one point to another one in less than 1 second. This is a fiction movie. So we are going to show that, okay, this is not only moving, but it can happen mathematically. How it can be done. So now let's start by the beginning. The question here is a matter of motion, how to move from one point to another one. The first formula that came to our mind is the Newton, the second law of the Newton, who said that, okay, if I have a system, the sum of all the interaction is equal to mass for acceleration of the system. This equation allowed us to determine all the trajectories of the system from one point to another one. Now, this equation of Newton was generalized by the French mathematician Louis Lagrange, who introduced what we call the Lagrangian mechanics. And he considered what we call the action. And when I have the system at this point, S of T prime, and we can consider a lot of trajectory from this point to here. And this sum of the trajectory is what we call the action. And this action can be mathematically written like that, which is the sum of over the Lagrangian. Lagrangian is a functional that is defined on the tangent space of the Euclidean space. And we can obtain the Hamiltonian, which is another functional, which is defined in the cotangent space or the phase space by from the Lagrangian functional through the Legendre transform. And if you have the action, the next one is to look for what is the minimum, to look for the minimum of the action by doing what we call the derivation or the functional derivation. And if we compute the functional derivation of the action, we get a differential equation, which we call the Euler-Lagrange. This equation tells us what is the minimum trajectory can join one point to another one. And another version of this equation is the Hamilton equation, which is given by this one. Here, at the first one, we use Lagrangian, the second one, we use the Hamiltonian. So these equations are equivalent. This is what we know about how to compute the trajectory of the system from one point to another one, which is the classical mechanics. Now, at the beginning of the 20th century, there is a new discovery, which is the science of the subatomic, which we call the quantum mechanics, who is the theory that led us to understand how the subparticle works. So to move from the classical world, we are in the classical world, to the quantum world, there is a map, but there is application that we say that we call the quantization. Quantization means that, okay, I have the function, the functional, and I have to transform this function to the theory of the operator that are not commutative. It's the way quantization, traditional quantization works. So another question that we can ask is, if we have the quantum world or we have the quantum system, how can I recover the corresponding classical system? The map, the inverse map here is called the dequantizations. The dequantization means, okay, I want to look what is the effect of the quantum world on the classical world. So the techniques that is used for example, for the quantizations is the solve eigenvalue problem, which is based on the Hamiltonian operator. And for the method of the quantization, the techniques that is used is a move from the operator to the classical variable, which this technique is we call the path integral or the quantum variational calculus. And the main operator here is the Lagrangian. The famous guy who introduced this variational calculus in the quantum mechanics is the Richard Feynman, who is a Nobel Prize in 1965. How he discovered this technique, what we call the path integral, and it's based on the youth experience that all we know. We have the source of beam here, and we will go through the dot slide. And at the end here, we have the stream we can find all the projection of the particles. So the goal is to to compute all the trajectory that the particle can take in this sentence. This gives the notion of or the calculus of the path integral. Now, the path integral, how is work? The path integral, you have here the particle, the state of the particle at the initial time, at the S prime position and time position, and the final state is here. So the path integral consists of compute the sum of the propagator. This is the propagator, which is the matrix of transition between the initial position to the final position. And this propagator is computed like that, which is the mean value of the time evolution operator, which is well known in the classical mechanics, in quantum mechanics. And the action that will determine or the classical path of the system is given by this equation, which is well known, which is the classical action. So the goal of this talk is to generalize this equation, or to generalize this classical value or this canonical value. So our goal is to generalize the path integral when we consider Heisenberg deforming Heisenberg algebra. And then once we determine, we generalize it, we can compute the corresponding path propagator and the action. And now from the action, we can determine the equation of the motion, and then after apply to a free particle. And so our approach, our technique that we'll use in this talk, it will be based on the Euclidean representation and the Fourier transform representation. So what all those means, we are going to see it in the body of the talk. So my presentation will be online like that. I will start by the canonical, the traditional notion about what we know by the Heisenberg algebra and the representation. After, we will generalize this notion. And from this representation, we will compute the path integral and determine the propagator and apply it for a special case, which is the free particle in this case. So when we talk about the position space representation, here we consider the Hilbert space. The Hilbert space is the space where we are going to work, where the quantum mechanics is defined. And we consider the emission operator, emission position operator, and the momentum operator that act on the unit vector S here. And the position operator act like a multiplication, and the momentum acts like a differential operator. And all these operators add a specific domain, which is the intersection of the domain of the operator S and the operator P. As a property from these representations, we have the identity operators, which is given here, and the orthogonality of the two unit vector, which is given here, the Dirac measure here, which is well known. Now, if I take some arbitrary vector in the Hilbert space and I project on this unit vector, I get what we call the position wave function, which is given. We determine the amplitude of the position of the particles. And now from this wave function, I repeat the action of the position operator S and the position operator P, which is given like this. And from that, from the position representation, we can determine the Fourier transform. The Fourier transform, the unit position vector is the momentum vector. So the Fourier transform of this is given by this equation, which is given here. And if you have the Fourier transform vector, we can determine the inverse. The inverse is given by the equation that is, 1 second, I cannot see my on my screen. Okay, which is given by the equation 6 here. And the orthogonality, the inner product of this Fourier vector is also given by the equation 7, and the compactness relation also is given here. All this notion is well known in the ordinary quantum mechanics. So now we are going to add now how the operator position and the momentum act on the momentum vector. Here we can find that, okay, the operator momentum acts like a multiplication in on eigenstate, and now the position momentum, the operator momentum position act like a differentiation on the momentum vector space. And at the end, we have by the equation 10, if I consider the wave function of the momentum, the action is repeat like that. This is what we know about the position and the momentum representation. From the above representation, we can propose what we call the Heisenberg algebra for any kind of the representation that we define. The Heisenberg algebra in one dimension precise is given by the equation 11. We can realize that, okay, the operator position are not do not commit here, and the position and the momentum commit. And from this algebra, we can determine the uncertainty principle, which said that, okay, we cannot measure the position and the momentum in the same time, which is given by the equation 12. This is what we know about the canonical quantum mechanics. So the goal in this talk is to generalize all this notion. So what we call position-deformed Heisenberg algebra. So what does it mean? Now we consider the ordinary Heisenberg algebra that we deform by the parameter tau by the operator. And we consider this part to be 0, since we are in one dimension. Now, in 2020, I proposed this algebra. And if I take tau, which is the parameter of the deformation of the space, I recover the ordinary Heisenberg algebra. So the position operator and the momentum operator can be written by the equation 14 given here, like this. And the action of this operator on the wave function, on the position wave function, is like that. And the momentum act like a derivation. Now we have a sort of a generalized derivation, which is, if I take the tau to be 0, we recover the deformed differential operator, the ordinary differential operator, given by the equation 15. Now, as a corollary, as a consequence of this equation is what? If we can realize that this operator position are emission, whereas the operator momentum, because of the deformation, are not emission. If I take, for example, tau to be 0, I recover the emissivity. So the consequence of that, the Hamiltonian of the system are not also emission. So if the Hamiltonian is not emission, it means that, okay, the spectrum of the system may be complex. We lost the unitarity, the time evolution of the unitarity of the time evolution of the operator, and the eigenstate of the system may be not orthogonal basis. So it means that the loss of the emissivity is impossible to do quantum mechanics. So we are facing the problem of non-Hermitian quantum mechanics. How to solve this problem? In a paper, we introduced this identity operator given by equation 16. This identity operator is deformed by the parameter tau. If I take the tau to be 0, I recover the traditional identity operator. And using this operator, we can show that, okay, the emissivity on the momentum operator are recovered by defining this domain of the position operator and the adjoint, with the condition that, okay, the domain of the position, the operator, the momentum operator is included in the domain of the adjoint. Now, as a consequence of this new identity, you have the orthogonality, the scalar product of two vectors that are taken in this domain is given like that. The orthogonality of the unit vector also is given, is generalized like that. And the generalized Heisenberg uncertainty principle is given, and a consequence at the end, we obtain equation 17, and which giving the minimum momentum and the maximal momentum. And now, from the above equation, the goal is to look for which the real eigenfunction of the momentum operator. And to look for this eigenfunction, we solve the equation, this differential equation given by 18. And the solution of this equation is given by 19 here, which is the equation that determines the wave function that the wave function that describes this position and this minimal momentum and the maximal uncertainties. So with this wave function, we are going to work with for this wave function and find what could be the properties of this wave function. So one of the important remarks is what? We realize that, in fact, this wave function 19 that we get are not physical. What does it mean by is not physical? It means that these functions are not square integrable. If I compute the norm from this operator, I realize that this norm diverge. And energy stability from this wave function also diverge. So from this both computation, the equation 19 that we got here are not physical. We have to look for another equation that we allowed, which will be physical and allowed us to continue our work. To do that, we realized that, okay, the problem is the domain that we consider. So what we did is we restricted the domain from the R to the finite domain, which is here, infinite domain, which is the minus maximal length to the plus maximal length before the deforming measure. And we repeat the later equation, we recover a new solution, which is given by equation 20. And if we repeat the above, the later computation, we realize that, okay, this wave function now is a square integrable. And the energy stability here also is also finite. So this means that equation 20 now is physical. It's the equation that we have to use, we will use in the forthcoming of the work. Now, once we guarantee the physicality of the wave function, now we can deduce some properties like existence for the new identity operators. We have realized that we can compute another new identity operator, which is given by 21. And these wave functions are not orthogonal, given by the 22. This non-orthogonality show a Gaussian distribution. As we can see here, if we take two different to the limit of two different eigenvalue at the infinite, we realize that, okay, is at the infinite, the wave function become the scalar product become orthogonal, and when we are close to the zero, is equal to 1. This show a sort of fluctuations there. So like you can see from this figure, when we go to the infinite, the wave function become 0. And when we come close to the 0, we have the 1. it shows Gaussian distribution. And this Gaussian distribution increase when I increase the parameter of the deformation in my space. And from this Gaussian distribution, we can show that, okay, there is a sort of a discreteness of the space, because if I take two different eigenvalues, the difference between them give me a sort of discrete value here with n element of C. So this shows that not only there is a fluctuation in my space, but my space, the eigenvalue that describe the space are discrete. And from this position eigenfunction, the goal now is to look for a Fourier transform. The Fourier transform is here, we consider an arbitrary vector which is integrable and the square integrable. And I project this function on our position representations. And it's giving me the equation 25. Please, 1 second, I'm coming. Please, can you make it? Sorry for this disruption. And I'm saying that computing the Fourier transform, I get the equation 25. And from the equation 25, which is the generalized Fourier transform, I can obtain now the inverse of the Fourier transform, which is giving me, which gave me here equation 26. Now, before this Fourier representation, the goal is now to look for how the later operator act on the Fourier transform representations. Like we can see here, if I take the position operator that act on the Fourier transform representation here, it gave me this one. The momentum also gave me this equation that is given. The Hamiltonian also on the Fourier transform representation is given by this equation. It is a sort of the generalization of what we know. Now, if I take the tau, the parameter of the deformation to be 0, I recover the ordinary quantum mechanic result in the momentum space, which is given me by this equation. Now, I have all the materials now to compute the path integral. Now, I want to compute the path integral on this generalized position representation and the Fourier representation. And to compute the path integral, the first thing to do is to know the Hamiltonian of your system. The Hamiltonian of the system for any system is given by equation 27. And from the Hamiltonian operator, we can determine, find the Schrödinger time-dependent Schrödinger equation, which is given by equation 28. And from this Schrödinger equation, we can determine the time evolution of the system. We have the position of the system at a certain time t, and the time at the initial is the time phi prime here. So the operator of the evolution here is given by the equation 19. If I add this operator of evolution on the initial state, I get a position state at arbitrary time t. Now, what we mean by path integral, according to this deformation, the path integral here is given by the equation 13. Here, the Q here is what we call the propagator, or the amplitude of the propagation. And if I take the tau to be 0 here, I recover the ordinary one. And like I said before, the kernel in Hamiltonian, or the amplitude of the propagator, is given by the mean value of the time evolution of the operator, which is given by 31. How the goal is to compute this propagator and now come to change it in the equation 30. Now, how to do that? We have our initial position, which is the L mass at the time prime. and the final position of the state is here. To do that is well known in the literature. We split the time and the position in the infinitesimal position and time. And now we compute for each split what is the evolution of the Hamiltonian in each split. And now from that, we take the limit of at the infinite to get what is the trajectory of the system. So as a resolution, we computed for the discrete propagator. The discrete propagator of this one is given by this equation that is here. And with a discrete action, we can realize that the discrete action is given by the equation that we have here. We still with our deformation here, parameter deformation. And as a lemma here, if I take the limit at the infinite, I get the propagator, which is given by the equation 32. And the continuous action is giving me the equation 32 here, like we can see, is generalized the original one that I discussed in the introduction of the talk. So if I take tau to be 0 here, if I take tau to be 0, I recover here the propagator at the ordinary case and the action in the ordinary case. Like the theorem say here, if I take tau to be 0, I realize that the deformed propagator is less than the ordinary propagator, which induces that the deformed action is less than the classical action. So we have here a sort of embedding. So because of the deformation, all the classical are embedding, all the classical trajectory are embedding in the ordinary one. So like I can show here through this figure, I take here, for example, the ordinary, let's say that this is our ordinary universe. And we have here the present, like I said at the beginning, here is the present, here is the future. And let's suppose that the ordinary action that we have is S0. So if I take the system to join the feature, it will move from here through the blue equation. Now, for the case that we have here is what? If I take account of the deformation, what I'm trying to say is that the deformation parameter tau will deform the space, will bend the space in this sense, in such a way that instead that the particle to use the Bruce trajectory, which is very long, they will use this trajectory, which is x here. As we can compare here, you can find that, okay, this trajectory in green here is less than the trajectory which is here. So it means that, okay, at the beginning, the question that I have asked is it possible to join Stellenbosch from Accra in 1 second? It means it's possible because if I want to take the normal trajectory, it's not possible. But if I take the hiding trajectory due to the deformation, and if I increase the deformation, we realize that, okay, the future and the present will become very close. And this allowed me now not to use the shortest part, the trajectory will consist of using the blue, this trajectory, which is S, which is a sort of the trajectory that currently we don't know if this trajectory exists. It's what we call what Einstein called the theory of the Einstein-Rosen theory, which consists of creating a shortest path between two systems. So if I come to the Einstein theory, which said that in the universe, there's no system which can go faster, and it means that, okay, if we are in this deformed space, the light, instead of using the blue trajectory and use this trajectory, it becomes very fast. You use short trajectory to join the future at a short time. it is something that very mysterious, and mathematically is what the above equation is meant. Now, as a consequence of this equation, now to determine which is kind of the trajectory, the equation that determines the trajectory of the system is that if we look for the minimization of this action, we realize that, okay, this is the equation that governs this shortened trajectory, which is the generalized Hamilton equation. From this position representation, now the goal also is to look what happened in the Fourier transform representation. And the path integral in the Fourier transform representation is given here. And the propagator in the Fourier transform representation is obtained like that. And the action is also given by here, by this equation. But on the Fourier transform representation, the physicality of this system is not very interesting. So we are not focused our attention on what happened on the Fourier transform. That is just a mathematical expression that we give here. So as an application of this result, we take a free particles. The free particles, the Hamiltonian of the free particles is given by equation 36. And I repeat the above equation, and I complete the propagator in the position representation is giving me by equation 37. The corresponding classical equation, a classical action, deformed classical action is given me by the equation 38. From the action, I can determine the kinetic energy. The kinetic energy from this deformed space for a system to move in this deformed space is given by equation 39. What we can realize is what? If I take tau to be 0, I realize that the propagator in this deformed space is less than the original propagator of the free particle, which induces that the action of this deformed propagator is less also than the ordinary action. And consequently, the kinetic energy of this system is less than the ordinary kinetic energy that we know in the ordinary Euclidean space. So now let's do this application. I take like this beautiful car here. I want to compute what is the corresponding kinetic energy in the ordinary Euclidean space and compared to the kinetic energy in the deformed space. As a result, I put all the results in this table. Here I have the ordinary equation, ordinary kinetic energy, which is given here. The mass of this car is a 12,482 kilogram. The time is 1 hour, and distance, we suppose that it ran for 15 kilometers. If we compute, the kinetic energy here is 8.7. And we know this car needs a fuel to run for this 15 kilometers. The price, currently the price of the fuel, 1 liter of the fuel is 1.8 euros. And for the 5 liters, let's say that is 9 euros. So to run for these 15 kilometers, we need at least 9 euros to get this energy, which is 8.7. Now compare now the result in our case for this energy. Here we have additional parameter, which is tau here. Let's face the tau to be 0.9 and compute the energy, the corresponding energy. We realize that, okay, this energy is very, very low than the energy which is here. The fuel that we need to run to get this energy is like a drop. It didn't reach the drop of of this fuel, which is 13 power of -6. liters. And in terms of the money, in terms of the price, this doesn't have its it doesn't reach even €1. It means that, okay, if we take account of this deforming parameter in the future, we don't need to use Fourier to get to run our system. And I try here to take different value of the parameter tau. Like I said, the parameter tau take value from the 0 to 1. If I take, for example, 0.1 here, the corresponding energy here is very, very less also. And the money that I need to buy this energy, for example, is €0.00498. And when I come close to the 0, I realize that I started getting the normal condition. So this result comes to tell us that there is something that exists in the universe by the future can replace the use of the Fourier energy that spoil our nature. And there's a sort of energy or force in the universe that will help us in the future to minimize the energy to do a lot of work. So to finish, I would like this, let me remember what Nikola Tesla has said. He said that, okay, electricity power is everywhere, present in a limited quantity, and can drive the world machinery without the need of the gold, gas, order, and the fuel. So I would like to end my talk by this citation and think about how this one can be implemented. For the moment, it's still a theory. Is it practical? I don't know. So let's what the future can decide for us. Thank you for the presentations.